Hi, Christian. How are you?
Hi, fine, thank you. Can you hear me?
Yes, I can hear you well. Can you hear me
Perfect.
well?
Yes.
Perfect. Um, yeah, we have a few minutes. I'll share on social media and everywhere that we are starting in the meantime. So, yeah, thank you. And thank you, everyone, for coming. And I'll introduce you, our guest speaker, in a few minutes. Thank you.
Hello.
Hi, Serena. How are you?
Good.
Meet Christian.
Hi.
Hi, Christian.
We will start in around 4 minutes. So thank you everyone for being patient, and again, thank you Christian for coming here today. This is such an interesting topic for me, and I think for many of our members here. We had these type of discussions, so we are really looking forward to your talk. So thank you.
Thank you for inviting me, and I'm really glad to be here with you.
It's a very interesting topic, and I'll mention ahead of time I'm prone to wander into astrocytes. but very interesting. And I think I'll take a sneak peek at the slides while we're waiting to get started.
Um, Albert, I'm trying to bring you up, but it's not working. So sometimes if you unlock and log in again, then it should work. Thank you. Okay, I think. Hi, Gilbert. How are you? Thank you for coming. Nice seeing you.
Hi, Gilbert.
I think we can slowly start and then, yeah, go from there. So, welcome everyone to the Science Society, and of course, a special welcome to Christian here. And thank you so much, Christian, for coming to Science Society. And before we start, I'll give you a little bit of an introduction so you get to know our speaker here today. So, Dr. Christian Piscicchia is a researcher at the Enrico Fermi Research Center, and he's the PI of the project Open Problems in Quantum Mechanics. And he is an expert in the development of phenomenological and theoretical models for the interpretation of high-precision X-ray spectroscopy data in quantum mechanics and nuclear physics. And I shared in the chat his website in case you wanted to check out projects he's working on and the really interesting research he's doing. And he is the national responsible for the experimentation in the Paul exclusion principle, VIP, at the National Institute of Nuclear Physics. And VIP established the strongest available constraints of several models of dynamical wave function collapse, as well as on models of spin statistic violations for electrons. He is also responsible for the Amadeus data analysis and a member of the Siddhartha 2 collaboration at the Collider in Italy, and of different collaborations at the J Park in Japan. He investigates pionization models for the study of the nuclear surface and the statistical mechanics of self-gravitating systems, and he explores the roles of strangeness in dark matter halos. During his career, he published more than 180 peer-reviewed papers, and he gave more than 40 invited talks, seminars, lectures, and colloquia. He organized 15 international conferences and workshops, and he's the editor of 2 special issues for the journal Symmetry, and is very active in scientific dissemination. He went to school. He did his master degree in astronomy and astrophysics at the University degli Studi in Roma, and where he also did his PhD. So we are very honored to have you here, so thank you again. And before we usually start, we ask a couple of interview questions, if that's okay with you.
Absolutely. Let me thank you all for inviting me. It's really a pleasure to be with you, and yeah, I'm amazed to be here, and I hope that this conversation, this talk will be interesting. Obviously, ask me whatever you are curious.
Perfect, thank you. Serena, do you want to ask the questions?
So certainly, yeah. So before we get to the body of your talk today, we usually like to give the audience a little personal side of you. So I'm curious. Do you have a particular memory that could go back to your childhood? But what might have sparked your original interests in getting into science?
Well, all my childhood long, honestly, I was very interested in philosophical items. I don't know, just to mention, yeah, meditation is something which was in my family since I remember. So that kind of questions, yes, kind of fundamental questions related to the topic of today about consciousness and relationship among matter and consciousness. Let's say that we discussed at home a lot. My decision to study physics was quite suffered, to be honest, because I was not as good as one can imagine that a person going to physics should be in mathematics. I was super scared about the first exams of mathematics, I remember. Yeah. Then paradoxically, I became more and more passionate in mathematics. At the end, my curriculum was mainly a mathematical physics curriculum. So I won this fear of the theory. And yeah, but I was not, honestly, I was not decided till the end. The first year, indeed, I followed contemporary courses in aesthetics at the Philosophy Academy in Rome, and contemporary the course in physics. Then, yeah, astrophysics. Then I found my way in astrophysics, and that really convinced me to stay in natural sciences.
Well, that's fascinating to think of, or the original contexts of coming into the world in a context of meditation and mysticism. Well, maybe that may not be the slant, but I mean, my own graduate work is in chemistry, but I never quite delved much into the nuclear world, beneath valence electrons and so forth. But I've always been fascinated in the topic that we're going to bring today. So I'm curious, is there a specific path? Take us from how you got to where you are today, in the sense of those experiences.
Well, also my career in physics touched a lot of arguments because, as it was mentioned by Katarina, I started with astrophysics. I'm still involved in some researches. Then I moved to nuclear physics during my PhD, and about 10 years ago, I had the possibility. I entered in contact with this very interesting experiment. I will speak a bit about. You will see it's very peculiar and unique in its conception, which is an experiment essentially exploring in general whatever kind of fundamental question we still have open in quantum mechanics, and there are, despite quantum mechanics is so well demonstrated experimentally, there are really foundational issues very deep in quantum mechanics which are still unsolved. And then this became my main topic, and this became somehow my experiment. Presently I lead it at the national level, and I succeeded to interest my institute, where now I have this project called directly Open Problems in Quantum Mechanics. And this particular relationship of quantumness and mind, to me, is absolutely recent. So it's a work which I started in collaboration with the colleagues who signed the paper with me. And is the first research in physics. I mean, so obviously, as I told you, my interest is quite old, but involving mathematical model and the data analysis is the first time that I approached the problem so directly, and I remained fascinated. And I have to say that in the last months I'm more and more involved in discussions of this kind, which are amazing, and I'm getting more and more passionate on this subject, which is difficult to unclose, because it's very difficult to be treated formally and experimentally, but I strongly believe that it deserves a lot of more effort in the future, and I will do for sure.
It's certainly a slippery slope, isn't it? Yes, so I think at this point we can launch into your talk. The audience can follow the slides, they're pinned at the top. And the moderators are here to, help run things. There'll be questions um, in the chat that we can take care of, and it's up to you whether you want to deliver a body of material first and then do a Q&A, or whether you want to let impromptu questions sort of guide the flow. So with that point, the mic is yours, and we'll make
Thank you very much. I hope I will remember to tell you each time I switch slide, or otherwise time by time remind me, because I used to forget. And yes, I think that at some point in the middle of the discussion, because I plan to give quite a long introduction to the case, at some point I will stop if somebody has already some curiosity to leave a bit of space for questions. So, okay.
Would it be possible to ask a question before you start, Doctor?
Sorry, there are questions before I start. I didn't get.
Yes. If I could ask a
Tell
question,
me.
if it's okay.
Yeah, sure.
Would you mind just giving a short summary of your talk?
Absolutely. Yeah. So I will start by outlining a bit what the model developed by Hamerov and Penrose is called the Orchestrated Objective Reduction model. what is based on. And essentially, I will end by telling you that the main point is the openness of quantum mechanics. So then that will take me some slides to describe this main problem of quantum mechanics, namely the collapse problem, the problem of measurement. And then, because it's very central to understand the orchestrated objective reduction, I will tell you the solution which is proposed by Penrose and Yoshi independently by these two physicists. I will tell you why the model is experimentally testable and what we did to do it, to test it. So I will speak a bit about our experiment. And then I will conclude with the main item. So how this measurement, which we performed, can tell something, can constrain, let's say, the various scenarios which were proposed by Hameroff and Penrose in order to explain consciousness, what, let's say, survives in this version of the Orch OR, which we analyzed, and what, on contrary, on the basis of this interpretation, can be ruled out. And then I will conclude with perspectives, because I prefer perspectives to conclusions, because I always like to look forward for what can one do more. Okay.
Thank you so much.
Okay. So this model essentially can be summarized in 3 points. So how consciousness emerges. Consciousness meant like choice. Up to Hameroff and Penrose, it depends on biologically orchestrated coherent quantum processes. All these words will be clear. In connection with microtubules, these structures which exist within brain neurons. So these coherent processes, which are ongoing up to the model in the mind, regulate the neuronal synaptic and membrane activity, and they evolve according to the quantum theory that we know. I will call it Schrödinger dynamics, till at some point is terminated according to a specific model of wave function collapse. Of Hameroff and Penrose speaks about objective reduction. So objective reduction means collapse. And this collapse model was developed by Penrose and Yoshi independently. It's called DP. I will call it DP from now on. But very important, I want to start from this question: why quantum mechanics was involved by Penrose and by Hameroff also? He's studying since decades the problem to have a role in consciousness. According to Penrose, he outlined this idea already in The Emperor's New Mind and then later in The Shadows of the Mind. He bases everything essentially on the Gödel's theorem. Starting from there, he says that there are aspects of consciousness, like understanding, that must to be beyond computability. So just to remind, Gödel demonstrated that whatever theory which is capable of proving basic arithmetic cannot be contemporary, consistent, and complete. So if we have a consistent theory, then you always can build some correct sentence, which inside that algebraic structure you cannot verify if it is really true, nor you can falsify it. So the theory is not complete. What, simplifying a lot, what Penrose says is okay, but Gödel's unprovable results are provable by humans, by mathematicians, which means that the human mind should not be describable as a formal proof system. So probably is running a non-computable algorithm. And where non-computability is from, that's the main point, is from quantum mechanics, where the incompleteness of quantum mechanics is represented by the measurement problem. Now, let me tell you that this kind of approach to the measurement in connection with consciousness is quite the reverse of what emerged in the very early period of quantum mechanics. There is a famous interpretation by von Neumann and Wigner in which they postulated that quantum mechanics can describe whatever in the physical world except mind, which should be treated like an external observer which is performing measurements. So quantum measurements occur as a result of the conscious intervention of an observer, of a human, maybe of an animal. There was a lot of discussion. Honestly, to be complete, I also have to mention that the same Wigner then disagreed with his own earlier interpretation, because first of all it could lead to some solipsistic interpretation of philosophical schemes, obviously led by this quantum mechanical reasoning, and also with the more technical problems related to how describing a perfectly isolated quantum system. But the main point is that what Hameroff and Penrose outlined is opposite somehow. And this is very amazing, the context in which this theory can be put, or developments of this theory will be put, in the sense that you have the feeling that biology evolved a structure in which is able to orchestrate and to couple to the neuronal activity these what they call physical proto-conscious events, and these are nothing but these quantum collapses, and these quantum collapses occur through the model developed by Penrose, by this DP model. So, since the measurement problem is very central, as I told you, I go now to describe a bit what we are speaking about. So I'm at slide 4. So I open this part of the talk. So 20th century, has seen the birth of what we consider, really the two basic pillars of physics, but of science in general, which are relativity and quantum mechanics, which both imply radical changes concerning our view of natural phenomena, the classical view of natural phenomena. Because in classical mechanics is really grounded on our perception of the world. So it's made of bodies, we call them material points, which live in a 3D Euclidean, so flat space, and this space is permeated by a universal time. And by these few ingredients, few ontological ingredients, you quite immediately arrive to the Galilean transformations and then to kinematics and dynamics. Relativity broke completely with the past. So we understood at some point that instantaneous communication is not possible. For example, action at distance of the fields is not possible, and that we have to admit that there is a highest possible velocity, the velocity of the light, and these represent an upper limit to the propagation of any physical action, also to information, to whatever. And this led to the conclusion that indeed space-time continuum is the correct framework for the description of natural processes. Relativity, both special and general, is a very close, self-consistent theory. We still didn't find any contradiction, nor at the theoretical nor experimental point of view, and is very different from quantum mechanics. Quantum mechanics, first of all, brought into the game chances at a very fundamental level. And then it shows how there exists an unavoidable limitation to the attainable knowledge about physical systems. I will tell a bit about this. So the debate about the interpretation of quantum mechanics started soon after the formulation of the theory, and is still ongoing. That's the point, and is grounded on the measurement problem, on the collapse problem. Imagine that it is not more than 20 years that physicists admitted that collapse problem is not solved. So it's really an open issue. Quantum mechanics, by the way, is an extremely powerful mathematical device. It's yielding the probabilities of the result of any conceivable measurement procedure, is the best experimentally demonstrated theory we have in our hands. But, and here I want to use the words of Bell, quantum mechanics tells us everything about what we find, but nothing is silent about what it is in the theory. So you see here 4 axioms. Now this slide is quite technical, but I will underline which are the points I really want to take home as a message. So we move from classical mechanics, from points in 3D space, to states described by some vectors which live in a completely abstract space. Now, what is important, obviously, are observable, what we can measure. And these observables are operators in this space, which, and what is important is the outcomes of the measurements of these operators, of these observables, are given by the results of their action on the vectors, on the state vectors, in particular on so-called eigenvectors, but this is not so important. Now, the second pillar, this is fundamental. If we know the initial state of a quantum system, then its state at any following time is completely determined by the Schrödinger equation. And this is an equation, you will see in a second, which tells you that the system evolves in a superposition of all the possible solutions of the equation. Now, if you want to know what's the probability to measure a particular outcome, n, then you have a mathematical tool to do it. It's not important. What is important is the fourth postulate. So what happens when you actually measure something? Because when you do that, you find one outcome, a real number, n, and then this superposition has to cease to exist, obviously, in the reality. And what happens is that is postulated, this is the famous postulate of collapse, that suddenly, instantaneously, this state vector collapses to what you measure, to the vector related to the outcome of your measurement. So go to the next slide. And here I summarize the first main problem of quantum mechanics. So the second postulate, the Schrödinger equation, mathematically is extremely simple indeed. And its mathematics tells us this strange behavior of quantum mechanics. First is first order. First order means that is deterministic, what I told you. If you know the state at time 0, you will know it forever. So quantum mechanics is not probabilistic at this level, it's completely deterministic in the dynamics, exactly like classical mechanics. Probability comes in because in this evolution of all the of the superposition of all the possible state, then you can calculate which are the probabilities of the outcomes. And where the superposition comes from, because again, it's very simple, this equation is linear, which means that if 1 and 2 are two solutions, then also whatever combination, alpha 1 and beta 2, is a solution, okay? Now the collapse. The collapse is completely the opposite. Is absolutely non-linear, because when you perform the measurement, you have this superposition and then it collapses to what you measure, 1 or 2. And is stochastic. Stochasticity is fundamental. It means that you have no chance to know before performing the measurement what will be the outcome. Okay. So the next slide I summarize in a table. The first main problem, the first phase of the measurement problem. So the theory is based on two completely contradicting dynamical principles. Now, next slide. Even more grave, quantum mechanics has big difficulty in speaking about properties. Not only about properties of microscopic systems, but, according to Schrödinger, even of macroscopic systems. This is an item debated, probably you know, by Einstein and his collaborators Podolsky and Rosen. who realized that the probabilistic character of the theory is intrinsically non-epistemic. And with this, I mean that do the case of statistical classical mechanics. There you speak of probabilities also, but the probability enter just because you have an ignorance about the state of the system. Because, for example, if you have a gas of billions of particles, you just can speak about mean quantities simply because you are not able even numerically to solve the equations, which are deterministics. Here, no. Here, the unknown is fundamental. Einstein says if, without in any way disturbing your quantum system, you can predict with certainty the value of a physical quantity, just in this case, there exists an element of reality which you can attach to this quantity. Okay? But this happens never in quantum mechanics because you are always in a superposition of possibilities. This has the extreme consequence that you even cannot assign at a given time a given position and a given momentum to a quantum state. This is a way to see the famous Heisenberg uncertainty. But, as you will see in a few seconds, one can almost never attach also the finite macro properties like location to macro objects. And this is almost incredible. Even worse, go to the next slide. There exist states in quantum mechanics called entangled states, very important in our Orch OR, for which even these individual systems possess no properties at all. An entangled state means that you cannot write the state as a product of the states which constitute it. No? So the constituents cannot be considered individually. You have to take it as a whole, which means that if you perform a measurement on one piece of your system, instantaneously you collapse the whole system, which means that you define precisely the outcome of whatever measurement you will do on another piece of the system, even if it's very far, even kilometers. Okay, this was experimentally tested. Despite this was obviously the main argument Einstein and collaborators to tell the inconsistency. This was their famous paradox. Luckily, this does not indeed lead to problems in causality, and this is essentially due to the stochasticity of the collapse, because you cannot preview what will be the result of your measurement, and in this way you cannot communicate instantaneously, so causality is preserved. So go to the next slide. Why Schrödinger allows for superposition of macroscopic objects, of tables? This was demonstrated, here I sketch a very simple demonstration by von Neumann. He tells, okay, imagine that you have an observable of some microscopic system and you measure with the macroscopic apparatus, M. M will be prepared in some ready state, 0, and then it will have possible states, for example, the positions of the pointer. You measure, imagine, I don't know, the mass, the length. Now, if you assume that Schrödinger is universal, then this means that, first of all, the interaction in between the microsystem you measure and the apparatus is linear. And second, that's fundamental because otherwise the measurement is meaningless, there should be a perfect correlation in between the state, the initial state of the system and the final outcome. No? Now, what's the consequence? If the initial state would be trivial, what never happens in quantum mechanics, just ON, then the final state is fine, is the superposition of the macro state N with the micro N. But what happens is that a quantum state is always in a superposition, like M plus N. This means that the final state is an entangled state. This means that the macro apparatus, your pointer, does not possess a macroscopic definite configuration, according to Schrödinger. Now the solution of the postulate, of the collapse postulate, is what I told you. Good, but at the act of measuring, all the possibilities die except what you measure. But this is not fine again, and leads to the second big problem of the collapse in quantum mechanics. So not only quantum mechanics seems to incorporate two dynamical principles which are absolutely inconsistent, but even deeper, it does not tell where the linear evolution ceases and the collapse takes place. So it doesn't tell you where the micro world, where the quantum real finishes and the classical world takes place. Okay, so this is very heavy. Also because, and here again I use the words of Bell, very famous, he said, but are not we obliged to admit that measurement processes are ongoing everywhere at every time? Absolutely yes, because measurement is nothing but interaction. So quantum object interacts continuously with the environment. And this leads me to slide 12 with the last concept, which is very important for us in Orch OR, which is environmental decoherence. So these peculiar characteristics of quantum mechanics, coherence, entanglement, are destroyed when the quantum system interacts with the environment. This is not a solution to the measurement problem. It's an apparent solution to the measurement problem in the sense that obviously when the quantum state decoheres through the interaction with the environment, it looks like collapsing, but like in a Chinese boxes play, you cannot continue this to the infinite. So the universe continues to be Schrödinger, and you cannot solve by this the measurement problem in general. So what are we speaking about? Coherence means the existence of a definite phase relationship between different states, which is preserved by Schrödinger and is absolutely necessary for quantum computing, is necessary for Orch OR. So if you look this in terms of isolation, the quantum state dynamics is not deterministic anymore, but the global evolution of the state plus the environment still remains, as I told you. What happens is that the components of the wave function of your subsystem decouple from this coherent evolution, and they acquire some random phases by the interaction with the environment, and this destroys the coherence. Okay, as I told you, the global wave function of the universe still remains unitary, still remains deterministic. So, for example, Penrose, in his paper with Hameroff, he argues, okay, this cannot be the solution to the collapse because, for example, how an isolated system would collapse? It could not. Or what's the nature of the isolation, or what's the size of the part which remains subject to the deterministic evolution? So, next slide. What Penrose, Dioschi, and many other people are trying to do is to introduce models which solve the collapse conundrum of quantum mechanics. In which way? Obviously, they have to preserve all those experimentally testable properties of quantum mechanics at the microscopic level, but they have to induce the objectification at the macroscopic level. So measurement-like processes have to have definite outcomes according to these new modified dynamics which these people is building. The number of people which in the last at least 50 years is working on this is huge, so I don't even want to mention. But let me mention the common characteristics of all these models. The common stuff is that the superposition should progressively break down as much as you glue together atoms to form larger and larger systems. And also that the modification of Schrödinger should be both nonlinear and stochastic, because these are the main inconsistencies, okay? Also, you can see that you have to do this in order to avoid, for example, faster than light signaling. So again, to fall into some non-causality of your theory. But the main question is what is triggering the collapse? And the answer of Penrose and Dioschi is what triggers the collapse is gravity. Let me tell a bit in more detail. So both them, Penrose and Dioschi, share this common denominator that space-time uncertainty destroys quantum coherence. This is a very old idea. It goes back to Feynman, just to tell you. Then it was developed like 50 years ago, some first model, and then many people tried to construct a mathematical model of this kind. There are many different mathematical models, approaches, different interpretations, but all of them have this common divisor, that the relationship among time uncertainty and energy decoherence leads to the collapse. Decoherence, we said, means the destruction of interference of this quantum coherently evolving state. When the observable is the energy, we speak about energy decoherence. Decoherence diminishes the coherent dispersion of the energy in this case. So imagine that too large coherent dispersion means that the system exhibits very strong quantum features. On contrary, if coherent dispersions are small, then the system looks classical. Okay, so we know that the coherence is necessary for the emergency of classicality from quantumness. But unfortunately, nature does not tell us what observable should be the primary one to induce the decoherence on the others and to cause the emergency of classicality. Classicality, in our context, read of consciousness. So the message of Penrose and Dioschi to take home is, if you would have a local time, even tiny indeterminacy, then this would induce decoherence on local energy. This would mean localization of massive objects. And this phenomenon appears like an exponential decay of the coherence, like the decay of quantum particles, okay, with a characteristic and predicted time, decay time, collapse time. I will call it tau. So, time uncertainty means the coherence, and the bigger the time dispersion, the faster the decay or the collapse it will happen, okay? But what's the relationship? So I told you at the beginning, Penrose and Dioschi ascribe the collapse to gravity. What's the relation of gravity with time uncertainty, with space-time uncertainty? The relation is quite one-to-one. I mean that in relativity, we know that what is called proper time interval is directly related to the metric tensor. The metric tensor is a mathematical quantity which describes the structure of the space-time, so of gravity, essentially. This means that a fluctuation of local time is one-to-one a fluctuation of the local gravitational potential. And from here came the visionary idea of DP. They asked themselves, but is not that maybe the gravitational potential should not be quantized? You know that what people in physics is trying to do since, again, 50 years, to put together quantum mechanics and general relativity is to quantize gravity, like in string theory, in loop quantum gravity. No, Penrose and Dioschi say, no, maybe it's the contrary. Maybe quantum mechanics requires an absolute indeterminacy of the gravitational field. So maybe, as I like to say, we have to gravitize quantum. So the point is that the gravitational potential is a stochastic variable. It has an indeterminacy. And Dioschi also demonstrated by a famous mental experiment that the intrinsic uncertainty of the mean gravitational field is inversely proportional to the volume of your space-time cell. This is the very link in between the relativistic argument of Penrose and the gravitational argument of Dioschi. So if you put this result of this experiment, of this mental experiment, in the mathematical model which Dioschi developed, this we call in the paper the simpler, with simpler Obviously, we don't want to underestimate. We just mean, and on this I will speak in the perspective that it can be extended. Okay, so if you put it in the model, you predict what is the decay time, what is the collapse time. I'm at slide 17, sorry. And here is the collapse time is the simple ratio, simple in this formula, in between h bar, the Planck reduced constant, and this energy difference. This is gravitational self-energy difference among the superposed state. What I mean with this complex phrase? I mean, imagine that you have a superposition, okay, between two mass distributions in two states. When the superposition becomes bigger and bigger, evolving in time, the corresponding collapse, this gravitational energy, which I'm speaking, becomes bigger and bigger. The collapse time becomes shorter and shorter, so the superposition at some point collapses. This is exactly the violation of quantum mechanics which induce the decoherence, which induces the collapse. Now, just to make you an example of how fascinating and successful is this model, if you calculate this tau for a proton, you find that the collapse time is 1 million of years. So the proton is absolutely a quantum object, obviously. If you redo that for a dust grain, small one, very small one, 10 to the minus 12 kilograms, you find that the collapse time is 10 to the minus 8 seconds. So the dust grain is classical. Indeed, I localize it, I see it, I perceive it with my eyes. Okay, so now to show you more how Penrose images this, go to slide 18. So we said reality is rooted in a three-dimensional space and a one-dimensional time, which are combined together in this four-dimensional space-time. Okay, we know that the space-time is curved. We know by Einstein, and that the curvature depends on the gravitational fields of all the mass densities, of all the distribution of densities. Each different choice of a mass density gives you a different space-time. Now imagine that you have a superposed quantum state for which the mass distribution has to differ, even slightly, okay? This will generate two different spacetimes. Now, if you have a mass in superposition of two locations, the spacetime would bifurcate. You will have the superposition of spacetimes, which is suppressed by general relativity. It evolves in time into spacetime branches. Their separation increases till at some point you reach a critical amount and these sheets die. Just one persists, the one which persists in the physical reality. And this happens over a precise mean time, tau, which I showed you. Unfortunately, this model, the DP, has a small problem. What's the problem? The problem is that if you take a point particle and you calculate this gravitational energy, this diverges. And this is absurd because a point particle is exactly what you imagine for a quantum object. And if the gravitational energy diverges, means that it collapses instantaneously, which is contradicting, is absurd. So they have to put in the theory a parameter. Okay, this parameter is called R0, is a cutoff length, which regularizes the theory, which avoids these divergences. The bigger this R0 parameter, the longer the collapse time, and this is the feature which is interesting for me, experimentalist, because my answer is, but okay, then can I test experimentally how big is this parameter? And hence, I can understand if the theory is really suitable to explain the collapse. The answer is yes, according to Dioschi. And here comes the, let me say, only conceptually difference in between Dioschi and Penrose. Dioschi, as I said, has a dynamics. He has a mathematics which describes the evolution of the states. And he predicts that the collapse causes emission of radiation. It's called spontaneous radiation. The reason is very, very simple to be understood. So we said that the gravitational field has fluctuations, is stochastic, no? That means that particles are accelerated. They move like in a Brownian motion, no? So there is a wiggling of the particles, and when a charged particle is accelerated, it emits electromagnetic radiation. Is unavoidable. This is extremely faint, extremely. This is why we still don't have a signal measured of collapse, but is an observable that we can test. And here comes the experiment. Moreover, the smaller is R0, the bigger is the expected radiation. So you can measure how big you expect R0 to be. Okay. Now, the difference with Penrose is that Penrose still does not have a dynamical development of his theory, and he's seeking for a theory which does not have this spontaneous radiation. This spontaneous radiation is related to a tiny energy non-conservation that he would like to avoid in his theory. But for the moment, this is the theory which we have in our hands, and so obviously, as experimentally, this is what we have to test. Okay. Then if you want on this, we can in deeper details, but for the moment, I would like to stop here and to leave some space for questions before the second part.
Yeah, thank you so much for the talk until this point. And yeah, please flash your microphones if you have questions of what we heard so far. Serena, go ahead.
So yeah, I guess at this point, and I'm sure you're going to get into R0 more intimately. But from the perspective of chemistry and more particularly organic chemistry, where um, certainly particles are always interacting. There's certainly quantum effects that are required to explain reaction distributions and which reactions will happen. Um, I'll be very curious, and perhaps I'll leave it as a comment, but maybe you want to give us some more insight into this R0 parameter, or how it, in what particular manifestations might occur at the molecular level.
Okay. This somehow the second part of the talk, not somehow, the second part of the talk will answer to your question in the particular case of these biological systems of the microtubules, because so where R0 enters in the play. R0 regulates the time of collapse, no, of this theory. So where it enters in biology, it enters where some biological system is taught, is supposed, is modeled to work according to a purely quantum phenomenon. So if you have some biological result, and there are many in literatures. I'm not an expert, but I know that are growing and growing the studies demonstrating that purely quantum correlated states lead, for example, in birds, the navigation, or in photosynthesis, or many other examples. So there, these R0 enters in the play because, as you will see in few slides, in order to be the collapse, the responsible for whatever kind of process, in this case the emergency of a conscious moment, you have to require that the collapse is caused by the specific collapse model that you have in mind. Penrose obviously takes his own, no? All these collapse models have to fight somehow against environmental decoherence. So you know very well that it was believed for tens of years that quantumness could not be involved in biology because biological matter is wet, is warm, and is very noisy. And all these conditions favor the disruption of quantum coherence and of entanglement due to the interaction, thermal or whatever, with the environment. So R0 is central in this point. R0 tells you if the biological quantum system can survive, for example, environmental decoherence, for a time long enough in order to be the genuine collapse to cause the emergence of the process. I hope that I interpreted well your question.
It does, and I wasn't too surprised that Penrose became fascinated with microtubules. I'd like to understand things at certainly at a small molecule level. There's more opportunities for these effects, but in terms of the more macro structures, with microtubules, they're quite rigid and have interesting dynamics, and I can see how if biology were to evolve a means of capitalizing on these effects, which sort of underlies the premise there, that they would have to have a reproducible rigidity with resonances and natural modes that could couple. So it's interesting. I can't wait for the rest of the talk. Thank you.
Yeah, absolutely. Obviously, I'm not an expert of neurobiology, so I cannot go very deep in commenting this. But yeah, as you know, when Penrose met Hameroff studies, exactly what he was fascinated. They evolved a lot. Their argument from this point of view, but I think that the state of the art is that they think that this pi electron resonance is from oscillating dipoles. So this is essentially the quantum superposition, that this can extend to the tubulins along the helical lattice, and more, even more, because they think that then the quantum entanglement, because the quantum superposition, this is the quantum superposition inside one neuron, for example, and then entanglement through the junctions can be responsible for even more orchestrated, articulated quantum global quantum coherent structures involving a lot, thousands of neurons. And this is exactly then the analysis, the point of the analysis which we did. So yes, I'm not an expert, but obviously they have very deep reasons for considering specifically the tubulins.
I have a question that I don't know if it's the right time for it or not, but I will say I have studied physics and the brain some, but it's been a long time, and this is very advanced and it's very fascinating. I'm amazed that people can even address these issues. But I was just wondering if you were to run into, say, a 14-year-old child or a grandmother who only got out of high school, and they wanted to know really briefly why this is important and what this might mean for either for philosophy or for science that's more practical, perhaps, or what would you say? Would you have an answer for them, or would you have to say, well, wait till you've studied physics or something? Anyway, thanks.
No. I would not answer good study physics. So obviously, in this context, I wanted to give an outline of the problem, coming a bit deeper into the roles of both the orchestrated Orch OR and then how and in which perspective you have to interpret our own experimental result and theoretical calculations on the Orch OR. But the Orch OR in general, then obviously I cannot, or better, I don't want to express to you my opinion if I have the feeling that is true or not, is so fascinating because, first of all, I think is one of the few non-mechanicists, not completely mechanicist, just because it relies on this non-computable foundational origin model of emergence of consciousness. It has implications from the point of view of evolution, for example, or from the point of view of explaining how much brain should be involved in the realization of more and more complex conscious moments, which for me is amazing. So it somehow explains why the structure of the brain evolved, no, in the structures which we have in present animals, in the humans, and so on, but opens the window. Obviously, this is a model which outlines a scheme of emergence of a complex, I would say, metaphysical concept, consciousness. But if true, if grounded on physical basis, it opens the possibilities for incredible developments in the centuries coming, because it relates to quantum computers somehow. So really the perspectives of the model, of this model, but in general the reason why investigating quantumness in mind in relationship to brain are unlimited, I think, and are incredibly fascinating.
Thank you.
I
Yeah,
think that
it's
we
fascinating. It's really got my brain challenged and interested. Thank you.
yeah, Joyce, my first year at university, I got a book called The Holographic Universe, and it's a really good read. It actually is good for the imagination while reading. And so, since reading this at a very young age, it like kind of primed my mind to be able to comprehend or think this way. So, if anyone's interested, it's a book called The Holographic Universe, Michael Talbot.
Yeah, sorry, it was a bit disturbed. I'm not sure if what was the question. So yeah, I'm not an expert, but I'm aware about this. This is another very interesting approach. I think it was developed originally by Pibram, and he collaborated also with Bohm, who obviously put a lot of the part concerning quantum mechanics. Yeah, they conjecture that brain processes have similarities with the storage of information in a hologram, and then they develop this holographic brain theory in which the brain is assimilated to a holographic storage network, and consciousness also here emerges somehow from quantumness, from quantum processes in between the brain cells. It's very fascinating.
So, if there aren't any other quick questions about the introductory part of the talk, perhaps we can move to the second half of the talk, and we'll have another Q&A after.
Okay, great. So summarizing where we arrived till now, my point was, okay, this model needs to introduce this cutoff, this R0, which is very central in the model, and as you will see, is central in testing the Orch OR. And my question was, can we test this R0? We can, because the theory is supposed to come with the emission of radiation. So the collapse comes with the emission of radiation, and the radiation is more and more abundant as much as R0 is small. And R0 was predicted at the beginning to be very small, to be of the order of the dimension of the diameter of a nucleus. So we are speaking about 10 to the minus 15 meters, okay? So what did we do? We had to design an experiment which is extremely sensitive to measure tiny, tiny signals over huge backgrounds. So the first thing, we performed it in what I like to call the cosmic silence. This is this amazing laboratory. Is an under mountain laboratory. It's called Gran Sasso because it's built in the heart of the Gran Sasso mountain in central Italy, where thousands of meters of granite rock shield the lab from the cosmic rays. The cosmic rays is this flux of particles, mainly light nuclei, which are investing the Earth constantly. They interact in the atmosphere, so they create cascades of particles not existing in the standard, in the common reality. These are muons, mostly on the Earth. And imagine that in the mountain, the flux of these muons, which we receive, our body is constantly traversed by these cosmic rays, is reduced of a factor 1 million. So this is the first necessary ingredient, because imagine that this background is huge at the sea level. For example, it's impossible to perform this experiment. So there in the mountain, what remains is the natural radioactivity. You know, the rocks radiate, have isotopes, they radiate. Then what we did, we calculated what is the expected rate of this spontaneous radiation predicted by the theory, okay? And this was very important because you have to imagine that this mathematical expression of the rate, what's the rate? The rate is the number of photons that you expect to measure per unit time per energy, okay? This depends a lot, for example, on the energy range in which you do the measurement. So we optimized our energy range in between 1 and 4 MeV. Okay, imagine that, for example, if the wavelength of this photon is bigger than the distance in between the emitted particles, then they emit quadratically. And this is exactly what we enhanced the expected rate by putting ourselves in this energy range. Okay, and this energy range exactly corresponds to a distance which is in between the nucleus and the dimension of the electronic orbits, these to avoid cancellations. Then I told you, you have to have the purest possible materials because you want to measure nothing. That's the goal of the experiment, essentially. So we use the detector, which is indeed the purest material existing on the Earth. Is an artificially produced crystal of germanium, and also we shielded it with layers and layers of ultra pure materials to shield them from this radiation from the rock inside the mountain. Also, we flashed it continuously with boiled nitrogen to keep everything at cryogenic temperatures, no? Because then the detector operates much better at very low temperatures. Still, despite, sorry, I'm at slide 25 now. Despite all this care which we put in the realization of the setup, you still measure something which is not new physics, is not necessarily the collapse, for example, but is few remained radionuclides, whatever, background which still survives all your efforts. So in order to be even more precise, we put on a simulation of all these physical apparatus, simulating all the known physically standard known emission processes which are ongoing in a virtual copy of our setup. No? And we succeeded to build a spectrum of what you expect to measure, which is known apart from the collapse, apart from the spontaneous radiation. So at the end, you put all this together, so your measure spectrum, the simulation, the theoretical prediction, everything, and you make a comparison based on some statistical model, a Bayesian model in this case. What we arrived to tell to the world? We arrived to tell, look, we cannot measure a signal of collapse. So this is called, technically, we don't measure a 3 sigma signal of collapse because we measured essentially 0. But by this 0, we can put an upper limit, a lower limit on the size of R0. Why? Because as I anticipated, the smaller R0, the biggest the radiation. So if you don't measure radiation, you can say, look, then it means that R0 is to be at least as big as, how much? As big as a hydrogen atom. This is enormously bigger than a nucleus, obviously. Is 10 to the 5 orders of magnitude bigger than the typical dimensions of a nucleus. In particular, this limit was 3 orders of magnitude bigger than the previous experimental results, and this sensitivity is enough, as you will see in a few slides, to tell something on the Orch OR. So let's go to the core of the Orch OR. So let's go to slide 29. Again, let me repeat the hypothesis. The hypothesis is that the wave function collapse takes place over a time, mean time, this tau, which is h bar over this gravitational self-energy. Then, the quantum superposition has to be orchestrated because biology, we have to be capable of integration computation, and very fundamental, it has to be isolated from the non-orchestrated environmental decoherence. This somehow was anticipated in a question before. What are we speaking about? We are speaking about that we need to have in coherent superposition a sufficient amount of microtubule materials such that this so that this self-gravitational energy, undisturbed by the environmental decoherence, results in a collapse on a time scale of the general order of a conscious experience. And Hameroff-Penrose take as order of magnitude tau should be of the order of half a second, 10 to the minus 2 seconds, obviously motivated by plenty of studies on EEG frequencies, visual gestures, reported conscious moments, and so on. Okay. So again, why is environmental decoherence so important? We remember that Penrose told that the process which leads to the emergence of consciousness has to be a non-computable process which should not be related to environmental decoherence, which is a random computable process. So in order for the basis of Orch OR to be effective, the reduction, the collapse of this collection of microtubules in coherent superposition has to occur through the specific Penrose collapse model. So environmental decoherence has to be avoided within at least the time tau of the emergence of the conscious experience. Now, we didn't go, and I will not go in details of this relation with environmental decoherence. Amerov and Perros, for example, in their review paper on Phys of Life Reviews of 2014, they report several studies for which quantum coherent behavior can be sustained in biological systems, even in these surprising conditions I was mentioning before. Now, to tell something familiar for whom is familiar with quantum computers, what's the parallel? In quantum computers, we know information is not just represented in bits, 1 and 0, but during this calculating process, which is deterministic, also quantum superpositions of both 0 and 1, the qubit, the quantum coherent superposition, and even large scale entanglements among qubits, enable to do this complex parallel processing. Then at some point, some quantum state reduction occurs, and the output is a definite classical bit, is a measurement. Now, in a pretty same fashion, this non-computable Diauchy-Penrose collapse would induce consciousness, and according to the studies of Hameroff, also before I commented a bit, the perfect actors for this coherent superposition to take place should be microtubules within the neurons. So very suitable candidate sites for quantum processing. So a moment of conscious experience, I'm in slide 31, emerges from a collapse event which destroys the coherence in this previously deterministically Schrödinger evolving quantum state of tubulins in neurons. These coherent quantum processes correlate and regulate the neuronal synaptic and membrane activity. So how we have to calculate the gravitational self-energy to put in our tau, no? We have to calculate from the difference between the mass distributions between two states of tubulin in superposition. But you know very well, matter is not homogeneous at all. The mass is concentrated in the nuclei. So Hameroff and Penrose suggest three ways to calculate this self-gravitational energy. For the superposition of the tubulin, you have these tubulins in this quantum superposition, coherent, separated at three possible levels. One, the first is called partial separation, which means the entire smoothed out protein. The second, at the level of the diameter of the atomic nuclei. And the third, at the level of the nucleons, of protons and neutrons inside the nuclei. But they say that the dominant effect should be the second one. Now, this separation, the nucleus of a carbon, the diameter of a carbon nucleus is 2.5 Fermi, 2.5 10 to the minus 15 meters, so 1 millionth of billionth of meter. The reason for carbon is complex. There is the obvious one, obviously. Carbon is the substantial component of chemical composition of the tubulins, but again, we said few words before. There are physical mechanisms in tubulins, according to Hameroff, that may be able to dynamically prepare these carbon nuclei into these coherent spatial superpositions of the order of a Fermi. The point is that we are at slide 32. Now calculate this collapse time. So calculate this self-gravitational energy. It has quite a simple form. Okay, you put the mass of the carbon, you put this separation, and to obtain how many tubulins you need in superposition, you have to divide by the number of carbons for each tubulin, 10,000, and for the number of tubulins which are needed. No? You equate this all to the time of a conscious experience, for example, your 25 milliseconds if you take 40 Hertz gamma synchrony conscious moment, and Hameroff and Penrose end up with 20 billions of tubulins. Now, one neuron contains 1 billion of tubulins, but they say just a fraction of tubulins per neuron are likely to really be involved in this quantum superposition. Namely, they say that fraction which is in dendrites and soma. And they take 0.1% of the tubulins per neuron to participate into this process, okay? To be coherent for 25 milliseconds, and then they end up, from the number I told you before, that you need 20,000 neurons, no, to be required to elicit this orchestrated reduction. Now, the fascinating point, as I told you before, if, for example, you would have smaller values of tau, you would need bigger amounts of brain. No, this is very interesting. So, if a conscious experience is deeper, somehow we can expect, then you need a bigger amount of mind involved in this experience. Now, what about, we said, assuming that the microtubule quantum state occur in a specific brain neuron, how could it involve microtubules in other neurons in the brain? Because you need 20, according to Hamerov and Penrose, 20,000. And as I said, they answer, okay, but you can have quantum states which extend by entanglement between many neurons through the gap junctions, for example. Okay, so they solve this way. Now arrives our measurement. So as I told you, we have in our hands a dynamical theory of gravity collapse, this is the Cauchy-Penrose, and by that, we have an experimental limit on our R0. So we can examine let me call it a version of the Orch OR, in which you take into account for these dynamics and you take into account for the fact that this decay time central in the development of the Orch OR is determined by the R0 parameter. Now the crucial point, I'm at slide 33, is that the three levels of spatial separation which are contemplated by Hamerov and Penrose exactly correspond to the levels of spatial resolution which are given by R0. And the collapse time crucially depends on R0. So, if we speak about partial separation, atomic nuclei separation, nucleon separation, this corresponds respectively to internuclear, to nuclear, subnuclear levels for R0. No? In particular, the result which I mentioned before, the 20,000 neurons, is obtained for the option called B by them. No? So when you require that the mass density resolution is as fine as the diameter of a carbon nucleus, 2.5 Fermi. But as I mentioned before, we put a limit which is extremely bigger. So we constrain R0 to be bigger than 5 times 10 to the minus 11 meters, so 10,000 times bigger than a carbon nuclear radius. Okay, and take into account that the larger is R0, much larger, we see, the longer is the collapse time. So what's the consequence? We go to slide 34. Apart from the calculation, which obviously is not straightforward, but the consequence it is. The consequence is that the mean collapse time for one tubulin becomes much bigger. Consider the fact that the nuclear separation is much, much smaller than this minimal resolution R0, you find that the collapse time for one tubulin is 10 to the 22 seconds. This means that the number of tubulins required to be in coherent superposition for a collapse time of, for example, 25 milliseconds is of the order of 10 to the 23. Now, remind that you have 10 to 9 tubulins per neuron, you have 10 billion of neurons per brain, and if you assume that, as Hamerov and Penrose suggest, 0.1% of the tubulins per each neuron are really involved in this quantum superposition, then you end up that you would need for to be collapsed for the emerging of a conscious moment 10 to the 17 neurons. Too many. Even if you assume that all the tubulins are involved from the neuron, still you are at 10 to the 14 neurons, which are many more than what are contained in the human brain, even if you assume obviously that this estimate is affected by an error, but consider that the lower limit which we put on R0 is a lower limit at 90% of probability, so the error is tiny. So following this consideration, it looks like the tubulin separation at the level of the atomic nuclei is not favored at all. It's discarded. Certainly also is ruled out the separation at the level of the nucleons, because in that case is even worse, so the collapse time is even larger. But then we analyzed the other scenario, the scenario called partial separation. So we took the whole smoothen out protein as an homogeneous bulk with the size L, and we analyzed the two possibilities you have in this case. You can have both, that this size of the microtubule is much bigger than of the tubulin, sorry, is much bigger than your spatial resolution. In this case, you still need huge amounts of brain, about 10% for a 25 millisecond collapse, and 1% if you take 500 milliseconds. While if the size that you take is of the order of the resolution of the R0, then you need 1 million order for 25 milliseconds conscious moment, or 10 to the 5 neurons for 500 milliseconds. So let me comment on this last number. Consider that this amount of matter is much bigger than whatever was actually realized in current superposition state laboratory, experiments achieved with optomechanics, macromolecular interference, and this kind. But here I really want to stress that we don't know if biological matter might find the way. There are many proposals. I'm not an expert, so I will not go into the detail, but the involvement of water or whatever biological mechanism could still sustain the survival of such amounts of mass against environmental decoherence. And this is somehow what, for example, it was underlined in the paper of 2014 and the following ones. I refer to this because it's a very nice review from Hamerov and Penrose. So let me go to the last slide. As I told, I want to call it perspective, because I think that the conclusions in the context that I made it very clear of our analysis, quite straightforward, is clear. What's the perspective? First of all, one of the typical questions is the Orch OR ruled out in general? And to this question, I answer clearly no, for two main reasons. First of all, as I said, this analysis relies on a version of the Orch OR in which we take a dynamical model, but Penrose is seeking for a mathematics for his idea, he hopes, which avoids spontaneous radiation. On this I can comment a bit, because it's a bit critical point. I just want to comment that spontaneous radiation, by the way, is foreseen by each model of dynamical collapse that we have in our hands till now. Tens of models which we have, all of them have this effect. And there are some very fundamental mathematical motivations for this. But obviously, Penrose is, first of all, you know very well, a Nobel Prize. And his idea moves from general relativity, while all the dynamical collapse models in our hands are presently non-relativistic. So obviously, if him or she or whomever else would succeed to develop a theory of collapse without this tiny energy non-conservation, this would be a significant breakthrough in our understanding of nature. And this obviously would mean that all the scenarios, not only the partial separation, would become far more plausible. But then I also would like to mention that, and this immediately involves perspectives in our work, in the group which did this analysis, and in my work. The model, this dynamical model which we used by Diyoshi, is ongoing, is being further and further developed. And what we are, for example, presently doing is looking for what are called dissipative and non-Markovian generalizations of this model. Just because, the physics proceeds like this. You have a model, then an experiment puts it in trouble. Our value for R0 is very, very big, so the model is in trouble. You need to extend the model. So the next step will be to, and this is what we are presently doing, to see what this means for the spontaneous radiation, these generalized models, and what it predicts for the Orch OR, which will be the consequences in the scenarios for the Orch OR. So, and with this, I conclude. Maybe I was also too long, so I hope that you enjoyed, and please ask me whatever curiosity you have.
Yes, thank you so much, Christian, for this really detailed and really amazing talk you gave. You explained really well all the theories behind. So we really appreciate that. And yeah, thank you. And yeah, please flash your microphones if you have a question. Serena, Dr. Shah.
Go ahead, Dr. Shah.
Thank you, Serena. Thank you so much, Christian. That was absolutely very amazing work, and it takes time that we understand it better. My question from you is about the coherence superposition that you just explained, and we know about the, conscious electromagnetic information, and there is a phase locking of the neurons, which is happening there. And you think that if we want to see that superposition as a matrix, does it explain the random matrix behavior? For example, if we want to see that, because I see that you put some couple of the equations there, and it just brought this idea into my mind. I was just wondering, what's your opinion about it?
Yes, it's very complex question, but I think that superposition can also explain this. Yes, I agree with you. Can be a hint for this kind of process.
Okay, so if anyone else want to ask a question, I can back if we have a time later. Thank you.
I have a question, but I'm just getting to a phone charger so my phone doesn't die.
Sorry, I cannot hear you anymore.
Oh, he just mentioned he's about to charge his phone
Okay.
before it dies.
Okay.
Well, so I had a question, and it comes from my thoughts on looking at microtubules and resonances and stuff. I was struck by a speaker that we had in some time ago that was looking at long-range oscillating dipole interactions that arise from natural modes in proteins. And the fascinating aspect to that was that if those natural modes are oscillating at close to the same frequency, there's a 1 over r cubed dependence rather than 1 over r to the sixth. And that was interesting in the sense that the long-range effect that they were able to measure experimentally on the order of 100 nanometers was suggestive of perhaps microtubules in resonance across different cells, and that an oscillating dipolar coupling could extend from different microtubules.
Oops, I lost you. I hope that I'm still connected. Can you hear me?
Yes, we can hear you, but Serena, I think Serena had some issues.
Okay. So from what I heard, yeah, extremely interesting this study that you mentioned. Indeed, 40 nanometers means more or less we are in the range, in the scale of ranges that we would need to motivate the Orch OR emergence. I would be curious to know for what are the time scales these quantum superposition was measured for how long?
Well, in this case, it was an experimental effect that would allow diffusible proteins that were in resonance to aggregate, and so that it wasn't a strictly diffusional mechanism. It was more of a driven type of diffusion.
I see.
But that was, and so they could, their dynamics over time would be affected by this process. But it's also interesting in the sense that even if just at the microtubule level, astrocytes also have the cytoskeleton component, and they are involved in driving neural synchrony and phase lock processes through resonating calcium waves, oscillating calcium waves. So there are, in terms of these other processes, there are many candidate mechanisms that could extend this range. But whether there's a necessary quantum effect there is an open question. And given a variety of mechanisms of extending resonance throughout the brain and driving thought processes and cognition, but particularly consciousness. Wonder what thoughts you might have on those opportunities, even in a classical sense, but what opportunities that may offer these quantum effects for in this context.
Yeah, I completely agree with you. This is a field fascinating from the experimental point of view in biological, biophysical, on really multifaceted world. You know that the main proposal for the falsifiability of Orch OR by Hameroff and Penrose is this to somehow experimentally test these interference bits into tubulins and microtubules, and then to search for some correlation between anesthetic damping of the bits. No? So if there is correlation in between the action of the anesthetic and the frequency of the quantum correlation. It is not very clear to me, so obviously this correlation is super clear and is fascinating. It's not clear to me how experimentally still this I was also discussing with expert in biology, biophysics, neurobiology, how to transport biological matter in a physics experiment of this kind, in a lab experiment of this kind. Because you know that Penrose was the first himself to propose an experiment to test his gravity-related collapse. No, he proposed to put in superposition an object of the finite mass, 10 to the minus, 12 kilograms, with a decay time which he expects to be comparable to the typical decoherence times. But as we know, all the experiments nowadays are far from that, or from the point of the view of the mass, or from the point of view of the distance of the superposition, or the time you keep the superposition on, and so on. But again, my main curiosity, I think what everybody thinks is that, by the way, even top laboratory experiment can tell nothing about biological matter, because some process in biological matter which we still don't know can be central, and we cannot reproduce it in laboratory. I don't know. So again, I'm not an expert, but this is my feeling.
Yeah, so a final question I thought was so curious about your value of R0 being about a half an angstrom. And that struck me as interesting in the sense that that's about a third of a carbon-hydrogen bond length. And I'm wondering, when I saw that number, I'm wondering, well, is that why we have so much certainty in chemistry? In that, molecular structure holds together so cleanly and predictably, except in cases that chemists love to construct. But any comment on the scale of your R0 parameter and its relation to molecular structure?
Unfortunately, it's not. It cannot be one-to-one related in such a straightforward way, because you have to imagine that the deep so this R0 has not really to do with the structure of matter, no, nor the quantumness of the structure of matter. It is a sort, you have to imagine, of smearing out of the quantum description of a wave path. Is the minimal resolution that you have on a stationary solution of the Schrödinger equation. I don't know if so. It's quite abstract as concept. How can I imagine that? For example, the first proposal of Penrose to solve this problem exists an equation which is very fascinating. It's called Schrödinger-Newton. You take the Schrödinger equation and you put a gravitational self-interaction term. No? So generally, gravitation is not considered in quantum mechanics because the effect of the coupling constant is too small to take it into account with respect to the other forces in quantum field theory. But the effect is the collapse, no? So if you put this, which is a nonlinear term, then at the end is not, it doesn't work completely as a collapse model, the Schrödinger-Newton, for various reasons, but is useful for a lot of things. And the very interesting thing is that if you solve this equation, you find like a basis. You find what are called solitonic solutions, stationary solutions, which mimic this basic resolution that you have on the quantum packet. If you allow me this description. So these are zero you have to take in this sense. Obviously, as I told you, it enters then in all the predictions of this collapse model. But then from here to relate it to chemistry, we are still far. It's a fascinating question, obviously, and we have to investigate. But the phenomenology of these collapse models is just right at the beginning. So now they are trying to explain why the collapse occurs. Then obviously you can compute, no, based on that. So because it can have an effect, no. The main point of all that introduction is quantum mechanics works perfectly, describes nature perfectly. But what if some parameters which are unknown in the present formulation of quantum mechanics can have, as you say, some effects on things that we measure, and maybe they are not just casual things. They are related to some hidden parameters in the theory, which we don't know because quantum mechanics is not the ultimate theory. It's a very good approximation.
Thank you.
Yeah, thank you so much for these answers and these questions. We had a while ago also a guest speaker talking about mechanisms of flavins and how they are these fundamental building blocks, and they demonstrated that flavin-based autofluorescence, they could measure them, and they were kind of magnetic field sensitive, and we also kind of um, discussed the electron spin selective recombination of these, and some, if there's maybe some quantum effects in living cells that are reflected in these building blocks. Are you did you ever think about flavins and take this, maybe calculate this in the model, if we would have less or more flavins available, and if that kind of would fit, be more realistic than the amount of microtubules that you calculated is quite a lot. So it's kind of, that's where we get the collapse from, that it's kind of too many that we would need to be realistic. So I was thinking, if you combine microtubules with flavins, if that would maybe be a more realistic combination.
That's a very good suggestion. Thank you. And I will ask you, I will put my email here on the chat, and I will ask you for the studies, so we can investigate what could be the yeah, if you also consider them not only microtubules, if these could make the scenario globally more realistic. Yeah, thank you for the suggestion. No, we still didn't study this.
Yeah, thank you so much. Carlos, Einar, and Kyle, did you have questions?
I have no questions. Thank you.
Sorry, I cannot hear you.
Yeah, I
I
think
was
you
going to
said.
say this is. I have no questions, but thank you so much for such an interesting talk.
Thank you.
Einar, did you have a question?
Yeah, hi everyone. So just a quick question. Because when it comes to consciousness and actually what relates to be conscious in what we in this class.
Sorry, I hear you really bad. Just a few words interrupted.
Yeah, you're in the matrix a bit.
Oh, sorry. Hear me now?
Barely.
Okay, I'll try again. When it comes to quantum part of um uh consciousness, which is basically related to human beings, as far as I've done this um the Gauss's flux theorem of gravity actually makes a difference. Is this involved?
Sorry, I couldn't understand exactly the question. I heard that you refer to some gravity theorem, but I didn't get. Maybe somebody else from the audience understood. Sorry, could you repeat?
It's, I've heard before, probably my connection. So pardon my connection. Yeah, sorry.
Yeah, you're breaking up. I can't quite hear it either.
Okay, no, I'm sorry, because maybe the question was related to quantum gravity. I didn't get.
Try again. It was related to Gauss's fluxus theorem of gravity. If it's related to atoms' behavior and superpositions and whatnot. Yeah.
Ah, sorry, okay. No, as far as I know, it's not, or still doesn't have connections which we investigated at the moment.
Thank you.
So yeah, it's great to hear your voice again. I kind of listened a lot more closely to what you were saying about radiation. And why I love this is because I can get creative with my philosophy. So like Wissam down there, for instance, I sent him a message. We are radiant beings in a radiant world, and because there's radiation all around us, and so one of the things that I really appreciated was that you're considering this, and you're considering this very carefully. So, the quantum theory absorption and emission of radiation announced in 1900 by Planck ushered in an era of modern physics. He proposed that all material systems can absorb or give off electromagnetic radiation only in chunks of energy, quanta E, that are these are proportional to the frequency of the radiation, E equals hb. The constant of proportionality, h, is also noted above, called Planck's constant. So I'm I'm really appreciative that you've actually considered this. First, quick question: did Penrose just omit it because he couldn't measure it? Is that why he omitted it?
Okay, so I answer first to this question. No. Penrose has a very... Can you hear me?
Loud and clear, yeah.
Sorry. No. Penrose didn't discard radiation because it didn't receive still an experimental evidence. He has a deep reason, and the deep reason is not trivial. So let me put it in this way. This radiation is related to a tiny energy non-conservation in the theory. Now you can imagine that when a physicist hears energy non-conservation, is not happy. No? Nobody of us could be happy about energy non-conservation. In reality, my opinion is much less critical on this from this point of view. Okay, I can mention, as I told you, very fundamental mathematical reasons related to the same structure of quantum mechanics why the radiation should be there, but I don't want to enter in that. I tell you another way. Imagine what happens with friction. No? In friction, you have the interaction of a system with an environment, and friction that is not related to energy non conservation is a false energy non-conservation, you know that this energy non-conservation is then recovered in hidden degrees of freedom. You have heating, no, for example. Now, what are we speaking here about? We are speaking about essentially the fact that quantum mechanics, this is a question more than, or obviously for me working in this kind of models is more than a question, but in general I want to leave it as a question. Is quantum mechanics the ultimate theory of nature? Maybe not, and we have strong evidences that is not. I tried to explain you the main reasons why we believe is not. If this is not, then there are degrees of freedom that we don't know. No, there are other models of collapse which are exactly hidden variable models, so-called, like Bohmian mechanics, for example. Just to mention an extremely interesting theory, the spontaneous radiation, so this tiny energy non-conservation, somebody relates to the dark energy. So now I don't want to say that this theory is correct or to prefer one to the other. It's just to mention that me personally, I'm not so critical for the existence of a tiny non-conservation in these generalized quantum mechanics models, because it could be related to effects which are comprehended, are understood in a higher, in a more general theory, which is up to come. These are phenomenological models. Obviously, the reasons of Penrose are serious. So it's clear that if he comes out with a consistent dynamical model which avoids these energy non-conservations and contemporary solves the measurement problem, then even better. There are so even better. It's questionable, but obviously we expect from a genius like he is to be absolutely capable to come with this solution soon. I hope that I answered to the question. There are fundamental reasons why people can dislike the radiation. There are as well very fundamental reasons why the radiation should be there. And if you want me to mention, the reason is that the collapse is Poissonian. Maybe you know that whatever decay of whatever quantum unstable state is exponential. The fact that it's exponential, like this collapse, is related to Poissonianity, is called, of the process in time. The fact that the process is Poissonian mathematically leads one-to-one, if you have this collapse time, to a diffusion equation, so to the fact that charged particles should emit. But this is a long debate, and I absolutely respect the point of view of Penrose, and somehow I also hope that he will come soon with a comprehensive theory without energy non-conservation. But I'm a fan of radiation as well, like you.
Amazing. When you feel like getting that in depth, it would be amazing if you would come back to this club and chat with us more, because what you mentioned about dark energy was deeper than I was going to go, but it was something that I was also looking into, because there's this theory and they utilize it more for cosmology, but I know that they're using the Hadron Collider to test some of it, but it's the rainbow gravity theory, that different wavelengths of light have different gravitational pull, or different gravity, force of gravity. So, or gravitational pull is the best way to say that. So I was thinking about the electromagnetic activity, and it's been hypothesized that there might be a little bit of light generated from that electromagnetic activity, and that could have something to do with quantum gravity. So I'll just land it there and not even go any deeper. But if you'd be open to coming back to this club and sharing some more time and energy, it would be very much appreciated.
Thank you very much. Thank you. Yeah, I'm open to discussions, obviously, and also I said I will leave the email, and if we want to discuss, I'm here. So I'm absolutely open and happy to. I'm really happy that I could interest you, and it's very interesting by the way what these points that you raised.
Thank you so much.
I just
Um,
try. You're amazing, though. So thank you so much.
yes, thank you so much. It's almost 2 hours that we are here, so I wanted to check with you. You probably need to leave. It's getting late for you. So I wanted to check in with you.
Yeah, if there are not urgent questions, unfortunately I forgot to put my email directly on the first slide. Indeed, it's very simple. It's my name, Christian.Piscicchia@CREF, which is my institute.it, but I will write it in the chat now. So yes, I'm in Rome, so here is 10 o'clock. Maybe we can address, if there are not very urgent questions, you can contact me privately, or I don't know, tell me.
Yes, and people can also reach out to me. I can share I can share then the questions with you or the email with you. So yeah, feel free everyone to reach out to us, and we really appreciate, Christian, the time you took for explaining everything so thoroughly
No, I
and to
do, I do. I appreciate your interest. I'm grateful for being here. It's a wonderful experience. So thank to you.
Yes, thank you so much, and enjoy your weekend and the rest of your summer. And thank you everyone for asking questions, interacting. This was a wonderful experience. So I appreciate everyone here, and again, special thanks to you, Christian. And maybe later in the year I can invite you back. It was such an honor. Thank you so much.
It's my honor. It's my honor. Thank you, and thanks everybody for the questions and for the participation.
Thank you,
Bye.
Christian. Wonderful
Bye.
talk. Take care.
Thank you. Bye bye.
Thank
Thank
you.
you. Bye.
Bye, everyone. I'll close the room in three,
You
two,
one.
one. Bye,
Bye.
everyone.